Because essentially what we're producing is a tiny, tiny planet between the tip of two diamonds.
You're listening to the Cosmic Cast.
Hi everyone, welcome back to the Cosmic Cast. Today we have the perfectly poached John Pernay Fisher.
Hello.
The slightly scrambled Elliot Carter.
Hello.
And myself, Marissa Lowe, the runny yolk. And we have a very special guest today. We have Dr. Eleanor Jennings from the University of Birkbeck. How are you doing, Ellie?
Hi, I'm great, thanks.
Well, after that fantastic intro, it's got me thinking about eggs. What's your favourite type of egg? I personally am a bit of a poached egg fan.
I enjoy a poached egg, but I have never successfully made one.
Yeah, they're tricky.
I only like them if
They're
someone else
tricky.
is making it for me.
Yeah, exactly. The man at Wetherspoons can do a good job.
Apparently meant to use very fresh ones.
Mm. But anyway, so you are an experimental petrologist.
I am.
So, and you've just started really at Birkbeck College. How long have you been there for now?
So I've been at Birkbeck since January last year. It's time that's gone by very, very quickly. I still feel like I've only just started. It's a lot to learn.
So this is your first lectureship post.
Yeah.
So you've come straight from a postdoc into a lectureship. How have you found that?
This is my first teaching post. So, I'm enjoying it a lot. Something that I'm really happy about is before you take on a job like this, you don't really know what it's going to feel like to teach. You know, you've been involved in teaching, you've kind of done tutorials, you've taught small groups of people, but you really don't know what it actually feels like to be a lecturer, to stand in front of a room and to teach. And I was nervous before my first lecture. I thought, what if I've made a huge mistake? What if I hate this? What if this is my job now? What if it's really unpleasant? You know, you go into this job without that kind of experience. And I just remember feeling so relieved on the bus home on the first day. And I thought, yes, that was so fun. I really enjoyed it. It was incredibly rewarding. And thank God it turns out now that I've taken on the job already that I actually enjoy being a lecturer. Yeah. So I enjoy teaching a lot more than I thought I would enjoy it, but I really like teaching.
Yeah. I mean, I guess it's an interesting point, really. I guess postdocs don't really get too much opportunity to practice teaching skills.
Which is a shame.
Yeah.
I think, and actually, if you are a postdoc and you're interested in following this kind of career path, if teaching opportunities come to you, you should take them, because, you know, people ask about those things in job interviews, and it's something, we're all in the same boat. No one has a good answer because no one has that much teaching experience. But the more experience you have, the more you know if you're making the right career choice, because it will be a big part of your life in the future. And the more you actually have things to talk about in your job interview when they're asking about teaching experience. So any opportunity that comes up, really, really do go for it.
I guess it's worth mentioning for the listeners that are perhaps not too familiar that Birkbeck is actually a night college. So I guess all your teaching has been in the evening so far?
Yeah, so I teach from 6 to 9 p.m, which is it can be quite challenging. It's important not to come into work too early, and it's important to have dinner before you start teaching, which I have learned the hard way. And I'm quite prone to a sneaky McDonald's on the way home on a Wednesday night, 10 p.m. when I finally get there. Yeah, so we teach in the evenings. So most of our students have jobs during the day, and some of them have sort of caring responsibilities or other reasons, and some of them maybe have disabilities. So we also teach a lot of distance learners, learners in other countries, learners who are learning from home. So about 60% of our students come into their lectures. It's quite different experience. You know, the students tend to be older. They tend to, maybe they're going through a career change. Maybe a lot of them already have a degree. Some of them have degrees in art subjects and they're trying to change their career. Some of them just need a degree to make some kind of career progression. Some of them are doing it for fun. Some are retired. Some are actually just out of school and they just prefer learning in the evenings. So it's a bit of a different atmosphere. It's not that different. You know, ultimately everyone's still learning about geology. The style, the content of our lectures is pretty similar to in other places. Students, I find that older students, they're very fun to teach. They tend to be more interactive. They're much more willing to put up their hand and to interrupt and to have some kind of dialogue with the lecturer when they want to know more about something. So it takes some getting used to being interrupted when you're sort of having a stream of thought and you're trying to teach. But actually it's much more fun, and I think it's a much more engaging style of teaching. So I enjoy that a lot. On the flip side, you know, some of those students, they can be very tired when they turn up. They might have been at work all day. Sometimes they miss their deadlines because they've had work commitments, they've had family commitments. So you also have to be a bit more understanding. You have to be a bit kinder to them sometimes. You know, you have to realise that their lives are a bit more difficult than those of some other students, not in every circumstance, but sometimes.
So what does a typical working day look like for you then? Do you normally do research during the day and then teaching in the evening?
I find it easier to have one day doing one kind of thing. So maybe on a teaching day, I like to spend the morning. Everyone in Birkbeck arrives at work quite late. We're not morning people. We do not employ morning people. So I probably get into work sometime between 10 and 10:30, which is shocking elsewhere, but whatever. Yeah, on a teaching day, I like to prepare teaching materials, have a look through them, maybe write up some lecture notes for the future, maybe think about exams, maybe try and update some of the literature, look at some papers. So I try and engage on teaching in those days. I think during term time it can feel very difficult to stay on top of research. You can feel very busy, but I think it's good to at least dedicate one day per week where you say this is a pure research day and this is where I'm going to really be in that right headspace where I can read papers and be really engaged on a particular topic.
Yeah, it is really difficult to sort of flip and flop between different papers. It's quite challenging, really, I find.
Absolutely. You need, to do research, you really have to be in that right headspace. You have to be really fully engaged in the topic you're doing. You can't skim through a paper and hope to get something deeper from it. Yeah. I find that difficult. I think a lot of academics don't get all that much research done during term time. It's just a case of having things tick over, and then when it's the summer, that's when you can get a bit more stuck in. But it's the time constraints are something that I'm still struggling with, and I feel that I haven't quite mastered this balance yet. So I'm hoping that I'll become more productive when I finally get a handle on, all of the additional responsibilities that I now have in my job.
Yeah, well, I imagine year on year, if you're doing the same sorts of modules, the same lectures every year, it'll get a bit easier.
Yeah, I hope so, yeah.
So you did your PhD in Cambridge, is that right? And then did you also do a postdoc in Cambridge as well, or?
No, so actually I'm going to start my career path 1 year before I started my PhD, because after I finished my undergraduate, that was in Bristol.
Oh, really? You're in Bristol.
Everyone's been through Bristol at some time.
Well, I'm from Bristol, so I'm very biased.
It's a brilliant city. It's a brilliant city, and I really, really enjoyed being a student there, I have to say. But actually, when I finished my undergraduate, I wasn't sure about doing a PhD, and I hadn't committed myself. I hadn't really applied for anything. And actually, I stayed behind for over a year, and I worked as a lab technician there in the experimental petrology labs. So in Bristol, they have a lot of experimental facilities. They have quite a big group. And this was a really brilliant experience because I learned a lot about all the different techniques they were using. I developed a lot of practical skills. I was helping other people with their experiments, but also I went to synchrotron trips. I helped people on their beam time. It was a very fun year, and it meant that, it really helped to clarify for me that I did want to follow a research path. So I'd say if you're not sure about going for a PhD, I really thought there was no harm in taking this extra year out. It also made my interviews incredibly easy. I had things to talk about. I had reasons, firm reasons I really knew that I wanted to do a PhD. And I had these practical lab skills that I could already sell as, something that I could do. So I really started my research career with 1.5 years of being a lab technician, and I loved it.
That's cool.
So then I moved to Cambridge. I did a PhD looking at igneous petrology of large igneous provinces, and specifically I was looking at the Paranaet and Decca province and thinking about the conditions that, the melting conditions that were happening in the plume, the chemistry of the mantle plume that formed that. That large igneous province is formed by the impact of a mantle plume starting head. It produced a lot of flood basalt and some other igneous materials.
So these are areas, I guess, for people who might not be too familiar, like Iceland and Hawaii, basically, these kind of large.
Oh, right, yeah.
Large
So
areas of
current
basaltic magnetism.
plumes that are well known, would be things like ocean islands like Hawaii and Hawaii and Iceland and Tristan and Samoa. There are plenty of them out there. But actually, when mantle plumes first arrive at the Earth's surface, they're probably much larger and much hotter than that plume tail that's forming those islands. So we get things called continental flood basalt. So they're huge, huge volumes of basalt. They're actually associated with extinction events. Most major extinction events that have happened on Earth have been associated with flood basalt eruptions. Even the extinction of the dinosaurs is a bit controversial because, there was the simultaneous impact of a meteorite that people think caused that extinction, but also on the other side of the planet. So that was in Mexico. But then in India, we have the Deccan Traps, which is a huge outpouring of basalt that has also been implicated for, causing the end Cretaceous extinction.
Yeah, it's still very argued. It's still very argued, and particularly for some of the more sort of unsure extinction events, like there was some in the 8-year scene, maybe. I think it's still very much argued whether it's impact related or.
And the thing is, a lot of impact craters on Earth have been lost, but it looks as though, some people, I think this is maybe taking it too far, but there is even some controversy about whether impact events are related to large igneous province events. Who knows? But certainly, large igneous provinces, there's a lot of volcanic gas coming out. It's a huge volume of magma. It's nothing like what we're seeing today. And people do think these are involved with extinctions. Okay, so that's a side point. That was a side point. But, I was looking at...
Because they have a big effect on, like, the global climate.
Yeah,
That's
they think it's through a
Carbon
climate-driven
dioxide
mechanism.
and
Yeah.
sulfur and all that being ejected.
Yeah, but I was interested in also whether we can see evidence for previous mantle recycling in that mantle source. So whether we can see, for example, if you'd had an ancient subducted plate, happening at subduction zones, if that ends up being sampled by a mantle plume from the lower mantle, and if that tells us something about whole mantle cycling of these kind of materials over long times. So that was a sort of geochemistry-focused PhD. There was a lot of modelling, thermodynamic modelling, imperial modelling, making measurements, analytical work. So for my postdoc, I moved to the Bayerisches Geoinstitut. So that's in Germany. It's the University of Bayreuth, and it's a research institute that's very much focused on experimental petrology and some other things. So I had access to all sorts of equipment there, doing experiments at different conditions, doing different analytical work. It's a great place to work. There's a lot of research money in Germany, so I would recommend, it's a good place to go for a postdoc. And then from that, so I worked there for a little over 2 years, and then I finally moved to Birkbeck, which is where I am now. And I have my fingers in a lot of pots, I feel, at the moment. I collaborate with a lot of people. I have some different projects on the go, and I think this is having this sort of broader set of interests has served me well, and I think it's kind of fun.
So it sounds like you had quite a straightforward path from PhD to a lectureship now. So was your postdoc only a year?
No, it was 2 years and 2 months.
Right. Okay.
But I did have a quite straightforward path, so I only did a single postdoc. So I feel very fortunate about this. And when I was doing my PhD, people constantly warned me, academic careers, it's very difficult. There are very few jobs. Most people will not get there. Don't get your hopes up too much, think about other things. And this kind of attitude got me down sometimes. And I would like to tell students now, actually, it doesn't always have to be this way. I know plenty of people who've managed to get academic jobs, who are enjoying themselves. It's not that awful. So, don't give up hope. I had quite a straightforward path. I've had a lot of luck, and I've had some good mentors, and I've had people who've been looking out for me. But, other people have those things too. So there's no reason why this kind of career can't work out for you. It can be a bit brutal. There are also, the job market isn't that easy, but it's not the end of the world. Don't give up before you've even tried. If this is the kind of job you want to do, then find some good mentors, talk to people about it. There's no reason why it shouldn't work out.
Yeah, being a PhD student now, a lot of what I hear is, it's so competitive, you're going to need to do X, Y, Z in order to put yourself in good standing to get a permanent job. I don't know what it's like for you, Elliot, but I just hear a lot about how competitive it is.
Yeah,
and that
a lot of anxiety.
It is competitive, and that attitude did put me off, but it turned out in the end it really wasn't that bad. Yeah. Some advice that I would have is I've switched fields a bit, and so from going from this surface igneous geochemistry through to this sort of deep planetary experimental approach, and this has served me very well. I think especially if you're going to work in a smaller department, having a wider range of expertise and research interests is something that can work well for you. So I think don't feel shy about switching fields. If you're getting to the end of your PhD, you don't have to do a postdoc in the exact same topic. You have some transferable skills there. So you should feel confident. If someone gives you the opportunity, you can feel confident and switch fields a bit. I think that's not something that I would discourage. For me, that worked out quite well. I attribute my easy career path partly to having made these kind of changes as I went.
Yeah, no, I think it's really good to sort of have a wide knowledge of stuff, and I think a lot of people think that whatever you do at your PhD, you've got to then carry on the rest of your career to do. And I think it's really good to go out there and get as much experience in different fields and different analytical techniques and stuff like that.
There are interesting problems everywhere. There's interesting science. There are interesting questions everywhere. You just have to either meet people who will direct you towards those, or at some point you have the experience to start to develop those for yourself. But there's interesting stuff everywhere. Don't think that what you're doing is the only important topic, because it's not, and it's not the only interesting topic. It's not the only thing that can grab you, and it's not the only thing that you can become an expert in. When you're a postdoc, the experience you have from your PhD is basically an experience in being able to learn things quickly, assimilate a lot of information, learn new skills. So when you're a postdoc, you can apply that to something new.
Yep.
I switched fields completely, and for about half a year, I found it very difficult. People were talking about people and papers and techniques that I wasn't really very familiar with. But you learn this stuff quickly, and by the end, this was my field now, and it was fine.
Yeah.
It was great to have the opportunity to do that. Not everyone will let you.
I mean, that's basically my experience as well, really, going from terrestrial PhD to a planetary postdoc. It was, as you say, it's like a few months of not really knowing, and then you soon get into the swing of it, really.
Yeah.
So what are your main research focuses at the moment?
Okay, so I have quite a broad set of research interests. So I started off from an earth science and a geology point of view. So originally my research was looking at, I guess my interests really are in anything to do with magma, but maybe more specifically the generation of magma in the mantle, what the chemistry of that magma can tell us about processes that have been happening in the mantle, melting processes, recycling processes, processes that happen in the crust, the way the magma changes its chemistry, fractionates, contaminates, how something that happens very deep down in the earth ends up relating to something that comes out on the surface of the earth. So that's kind of my background. I then broadened a little bit into asking questions more about sort of whole planetary geochemistry, which again is actually a magmatic process in a way. You could say, well, in the beginning we had phases where the earth was partially molten, and how can we interpret processes that happened then, metal segregated from that magma, and it left a geochemical imprint on that magma. So how can we now look at the chemistry of the earth and say something about the ways in which it formed? So these research interests, they're pretty broad, and there's no reason that they are constrained just to the earth. I mean, the earth is just a planet. It's like any other planet, we just know more about it. So we can base a lot of our knowledge on processes that happen here. But I'm starting to get more interested now in looking at other planets, in looking at igneous materials that we have on the surfaces of other planets, and how we can interpret their chemistry, using the sort of frameworks that we're using on Earth, but maybe going into systems which are less well constrained, where we don't quite know about the processes that happened. Sorry, this was a very sort of broad and rambling answer, I guess, but I can be interested in anything that's encompassed by pretty much the chemistry of magmas.
Yeah. So processes like planetary differentiation, where a planet's starting off molten and splitting off into different layers, but also magma creation, magma ascent, and all that.
Absolutely.
If they're universal processes, it makes sense to take Earth as a nice test case and then start applying it in other places.
So I've started now working on some samples some Shergotite samples. So these are meteorites that we think come from Mars. And I've also started working on some lunar basalt samples. And so the idea behind working on these is pretty much we have the expertise to know how we would interpret these in quite a lot of detail in the Earth. And actually there's a lot of scope out there for taking these materials from other planets and really starting to think more carefully about what those materials mean in terms of the interior of those planets, how those materials can tell us more about the big picture of what's going on. So I'm sort of returning to my roots a bit in moving back to more taking material from the surface of planets and talking about processes that might form those.
So you'll be using experimental methods then to address some of these questions, or?
Right, yeah. So I use a mixture of experimental approaches, so creating mini rocks in laboratories. So I guess I can talk some more about this. But I also do analytical work, so I take natural samples and make various measurements of what their chemistry is. And I also do quite a bit of modelling, so we can use thermodynamic models and we can use empirical models to try and take that data and do something a bit more quantitative with it to really be able to interpret it rather than just having a quick look. So my favourite approaches kind of combine all of these. So maybe you make some careful measurements, you have the chemistry of materials, and then you think, well, what does this chemistry mean? We need a framework in which to interpret this. So we can do some experiments so that we can constrain these different processes and we can look at the trends we might expect in chemical data that different processes give us to look at these samples. And then we can use that experimental data, feed it into thermodynamic models, and then use that model to really extrapolate and interpolate between the different conditions of the experiments and try and have something more universal to work with. So this is my favourite sort of approach. Experiments are the most fun part of it, maybe the most interesting, and maybe the one that people know the least about, although it sounds like you've had some people on this podcast previously talk about experiments.
Yeah, well, so I guess David talked more about some of the lower end pressures and stuff, but I guess you've done a lot of work with quite high pressure stuff, which is quite interesting. So I guess it's quite cool. So you use diamonds to get high pressures.
Yeah,
right?
So one of the research themes that I've been involved in is looking at the formation of the Earth's core and how that's segregated out from the mantle, or also the cores and mantles of other planets. So obviously the pressures and temperatures at which that happen can be extremely high. We actually don't know exactly what the pressures and temperatures are, but they're very, very high. And so for the kind of experiments that we use to look at igneous systems, we don't really reach those extreme temperatures and pressures that we find in deep planetary interiors. So one of the types of experiments that I've been involved in that we do, they're known as diamond anvil cell experiments. They can be quite challenging to do. So essentially what we do is we take 2 diamonds, gem quality diamonds, and they have truncated tips. And so we wedge a tiny, tiny piece of sample between the tips of those 2 diamonds. You know, there's an apparatus to hold this thing together, but essentially it's a tiny sample wedged between the tips of those diamonds. And of course, if you apply a pressure to the back of those diamonds, you're translating that force down to a very, very tiny area, and then the pressure you get between the diamonds, you can very quickly generate enormous pressures. You don't want to go too high, because if you go above about 100 gigapascals, those diamonds pretty much break every time. A very expensive way of getting through research. But we routinely go up to about 80 or 90 gigapascals, and the Earth's core mantle boundary is something like 120 to 130 gigapascals. So we're getting close to those conditions.
So it's pretty. So in terms of depth, I guess that's hundreds of kilometers deep.
I mean, we're talking about the lower mantle, so we're talking about deeper than 600, 700 kilometers. I mean, in reality, core formation obviously happens sequentially, you know. So we start off with very small planets, and as they grow, the pressures at which that metal is segregating out from the silicate and forming that core is getting larger and larger through time. So actually, it's not that low pressure experiments aren't relevant, but to very large planets, to look at the final stages of core formation, we need to get to these very extreme conditions. So because the diamonds are see-through, we can just fire an infrared laser through them, and as long as it's interacting properly with the sample, if the sample's got metal in it, it can heat up extremely easily. So getting to very high temperatures is not difficult. Controlling the temperatures is difficult, but reaching them, you zap it with a laser, job done. You can reach 5,000 Kelvin in a few seconds.
So
if you're not careful.
Quite short experiments then? Is it just a sort of a laser pulse, things melt?
It's not quite a laser pulse, but if we're dealing with liquids, the diffusion rates are so extremely high at those very high temperatures that you really don't need an experiment to run for very long to reach chemical equilibrium. So sometimes, 30 seconds, a minute is fine. And actually, if you're dealing with experiments with a liquid metal and a liquid silicate being heated by a laser, they can be quite difficult to control, because these things can move around, and of course if the metal moves away from the laser spot, it'll cool down very quickly. If it moves into the laser spot, it can flash heat. So actually if you run these experiments for too long, you can run into a whole load of other difficulties. So we try to keep the experiments quite short.
So if you're doing all this on the tip of a diamond, how small are these volumes of experiments you're doing?
Oh, they're tiny. I mean, it's quite fun in a way, because essentially what we're producing is a tiny, tiny planet between the tip of 2 diamonds, and that planet is probably about 10 microns across. I would like to compare this to the width of the human hair, but I don't know how wide a human hair is.
About 100 microns.
100 microns. Oh, fantastic. So actually so we're making a tiny planet that is 1/10 of the width of a human hair between the tips of those diamonds.
That's incredible, really.
How do you prepare the things to go between the diamonds? They must be quite small to start with, right?
So the rules would be no caffeine, no sugar, no alcohol. Don't do it when you're too hungry. Don't do it when you're too full. Don't do it when you're stressed. Don't do it if you've just done exercise. So, there are a small number of windows in the day when your hands are steady enough that you can manipulate these things. So there are different ways to prepare it. We'll squeeze a piece of rhenium metal, or sometimes other metals, between 2 diamonds.
Why rhenium?
Rhenium is very stiff, and it's very unreactive. We'll squeeze it between the diamonds to make a pit. We'll drill a tiny hole that will be the sample chamber. So the rhenium's it's supporting the tips of the diamonds. It's stopping them deform too much. It's stopping them break, and it's holding everything together. And then we have a tiny well in the middle where we can fill it with our sample material. So some people will just do experiments. They'll look at phase relationships. They might put in a powder that's like the mantle, and they'll put it in there, and that's not too difficult to prepare. You're just stuffing a powder in. These experiments are quite difficult to prepare. Sometimes we'll put in a disc of silicate, so it'll be something that's very, very thinly polished. We might polish it to 10 microns thick, cut out tiny circles using a laser, try and pick it up with the tip of a needle, a very sharp needle, and drop it in the hole. And then I'll drop in a very thin piece of foil, metal foil. I'll try and squeeze that and rip a bit off and kind of get it in. It's quite difficult. You need such steady hands. You have to, and then I'll put the final disc of silicate in. Sometimes we'll put in a chip of ruby because we use ruby to monitor what the pressure is. And sometimes you'll have extra layers on the outside that act as pressure mediums to give more hydrostatic pressure or to help with the temperature distribution. These things are very tiny. You load these cells up down a microscope.
So can you see them with your naked eye?
No.
Wow, okay.
The material on the tips of the diamonds you can't really see with the naked eye. So we load them up down quite powerful microscopes. We're usually doing it by hand, so really you have to understand your body well enough that you know the times of the day, that your hands are steady enough that you can actually drop this disc in the well. Sometimes you have to try and do it 5 times. You'll try and load it, you'll make a mistake, you'll stab the needle in, you'll miss it, you kind of clean everything out, try again. It can be quite challenging. On the flip side, the experiment's very quick to do. Then the other challenging part, of course, is that your experiment is so tiny that really doing the heating experiment is only the start. We're interested in the equilibrium chemistry. There's not really a good in situ way to measure this during the experiment, so we have to do the experiment, heat it, quench it, so turn the laser off, everything freezes, the chemistry is frozen into that metal phase and the silicate. Then we have to take those out, somehow cut them open, and somehow measure those tiny, tiny phases and get some fairly accurate measurement of what the chemistry is. Do this at different pressure and temperature conditions and try and constrain how this chemical behavior, how the distribution of different elements will change with pressure and temperature. The chemical measurements are the more challenging part because they're just slightly smaller than the kind of things that we're typically skilled at analysing in geochemistry.
Yeah, I can't remember if we've talked much about SIMS and laser ablation methods on this podcast before, but I guess there would be some more routine measurements, but I guess they're too big to do.
They're too big. So laser ablation, we might have a spot size somewhere between 30 and 60 microns, maybe bigger, depending on what you're doing. So maybe the metal in these experiments might be 5 to 10 microns across. Maybe the silicate is just a couple of microns rim around that. So we can't use any techniques that involve firing a massive laser pit through something. SIMS is too big as well. Nanosims is better. So nanosims, we don't quite have the same sensitivity in terms of looking at very low concentrations, but we do have a much higher spatial resolution. And nanosims we can use to measure light elements as well. So that's great. So that's one technique that is possible to use. It's still, it's not used very routinely for these experiments. These experiments are not that routinely done. They are difficult. They are considered difficult. We also use the electron microprobe, but again, we're really looking at the spatial limitations of the electron microprobe. So although we can make microprobe measurements, and people are more familiar with this technique, there are some special limitations that we don't usually have to think about that we really do have to account for when we're measuring very, very small things by microprobe. We've also tried doing atom probe measurements.
Yes, the atom probe. That's definitely worth talking about because this is a very cool thing. I don't know if you guys are aware of what an atom probe is.
I've never seen an atom probe.
But I guess it's where we were talking about this yesterday. Actually, it's a relatively new instrument in the world of Earth sciences. But I'm sure you can tell us more about it.
Oh, the atom probe is a spectacular instrument. It's also a very, very difficult technique to use. But it's one of these sort of high risk, high rewards. If you can get it to work, even if you just have 1 or 2 measurements, you really have the opportunity to find out something very interesting. So if you ever have the opportunity or a reason to think maybe atom probe would be good here, I would really urge you to consider it. So the atom probe essentially will measure atom by atom. It will measure the identity of individual atoms and it will give you their 3D positions.
But in individual isotopes,
Wow.
basically.
Yeah. So it's a tiny, it ultimately measures things using a time of flight mass spec, so it can identify individual isotopes. It has a pretty high, what would be the word? Of the number of atoms going into it, I think the recovery, so the number of atoms that they're actually able to measure is about 50% of them. So the samples that you measure are tiny. You would use atom probe to look at things on a nanometer scale. So we're using it to look at some unusual textures that we find in these diamond anvil cell experiments. And we have some strange exsolutions textures on the scale of tens to hundreds of nanometers. So for the atom probe, you would cut your sample into a tiny needle. So the tip of that needle would be about 13 nanometers across. And the length of it that you'll end up analysing might be 100 nanometers, up to a few hundred nanometers if you're lucky. So you cut it on something called a focused ion beam. So it's like an SEM with an extra beam of gallium ions that you can use to cut things. So you make these very tiny needle tips, and then in the atom probe, you evaporate the atoms off the tip of that needle, atom by atom, and then its 2D location when it arrives at the mass spec, as well as the relative timing of the different atoms arriving there, allow you to reconstruct this 3-dimensional map. So you have a very, it's not something you can use for routine measurements. It's difficult, it's expensive. It's especially difficult on non-conducting samples. So in the earth sciences, if you're looking at silicate minerals, this is something that's being developed in atom probe technology, but it's something at the limitation. It's much easier to work with metals. And you need a very specific reason to really be looking at that nanometer scale. But it's an extremely powerful technique, and it makes some very pretty images.
Yeah. I seem to remember, have people done it on zircons to do like really small lead dating on? I think they may have done it on Jack Hill's, maybe.
So there was a very high-profile paper. I'll try and remember the details of this.
I remember.
I think what they did was they looked at the distribution of lead within the zircon, because essentially when people are measuring uranium lead dates on zircons, they consider it like a bulk tech. They have a laser spot size that's fairly large, and they say, well, this is the age we get according to the amount of uranium, the amount of lead, or actually the amount of lead. But when they were looking in a lot of detail, they found that the lead was not uniformly distributed across the zircon. It was really clustered. And so this leads to some questions, how, I guess it leads to some questions about the robustness of the technique. You're doing something on a larger scale. When you zoom in and look at that fine scale, does it support the interpretations that you've previously been making? I think there might be a lot of disappointment that comes up when we start looking at things at those scales. We might find that some of the techniques we've previously been using, there might be some additional complications that we haven't quite been thinking about. It would be interesting to see what comes up. I know people have also been doing some dating using bedellite, I think, by atom probe.
Yeah.
I have a feeling this has been done in the UK.
Yeah, I can't quite remember. So bedellite is another sort of zircon-bearing mineral that's quite often used as a shock indicator, particularly for Martian samples. But so where have you done your atom probe? Is there an atom probe in the UK? Or have you,
so I did this in the materials science department in the University of Oxford.
Oh, okay, right.
I don't think there are very many atom probes in the UK. They're extremely expensive instruments, and they take a lot of expertise to run. But I had a great experience doing this in Oxford. So they are materials scientists. They more traditionally work on things like steels and also sort of high-tech materials, things like for solar panel type materials. It's often used to look at things like defect structures, maybe trace elements sitting in defects or at grain boundaries, like things on that kind of scale. But I think there's definitely a movement at the moment towards using this technique a little bit more often for earth science type applications. And as long as we can, be good at measuring non-conductive samples, which has really been the limitation in the past, then this is something that could open up to earth sciences.
Yeah, and I guess with all these things, as time goes on, people will get more familiar with these methods, and it'll become slightly easier to.
It'll still be expensive.
Yeah.
But it's something usually. My most commonly used method is electron probe, and on the electron probe we can make hundreds and hundreds of measurements in a day, and we often think about sort of statistics and data sets and developing a big data set. It's just a very different approach to obtaining data, because we're really just talking about getting a single data point almost, but where there's something important about that spatial distribution, and where you can say something. Maybe you can just make a particular measurement that says something more general about the others. So for me, it's quite a different approach towards obtaining data. But it's a specialist application, but I'm sure there's more that we can use it for, that we just need to be a little bit creative and imaginative about.
So there's one last question just before we wrap up that we try and ask all our guests, and that is, are there any other sort of interests outside the field of science? So if you weren't an academic, what else do you think you might be doing?
So when I was occasionally during my PhD thinking about what else could I do, again, because of this kind of negative attitude you hear as a PhD student about the disaster that is an academic career. So I started thinking, well, what's my backup plan? What do I enjoy doing? I would have become a data scientist at that point. I didn't used to know very much. I was never a computing person. I never was that gifted with computers. I never knew that much about them. But when I was doing my PhD, I really started to do a lot of modelling. I taught myself a bit of coding. I really enjoyed it a lot. It was almost therapeutic. I quite like the aspect where your code is broken and you try and find, you find what's wrong with it and then you fix it and it feels really good and you've kind of solved your own problems. I'm quite interested in problem solving. I think in the world out there is a lot of opportunity in data science. A lot of companies are struggling to find enough good data scientists to fill their roles.
Mhm.
It's a field that's especially open to women. We really need more women data scientists, and people are looking to recruit them. If you're a scientist at the moment, you have the transferable skills potentially that you can develop your coding a bit. There are plenty of courses out there. There are plenty of schemes set up to take people out of academia and place them in data science. I know people who've gone down these routes, and it looked really interesting. You work on real world problems that are super interesting. It's almost like a PhD. You have your problem, you have your data, you can have a think about it, you can decide how to approach that. I was really quite interested in doing this as a backup career. The other one is that I used to want to be a ballerina, but I was really, really bad at dancing, so I guess that was more off the table.
So that's the most extreme career change you've had then.
Yeah. I'm trying to think what else. Actually, every step of the way, I've never really thought that much about long-term careers. I've just kind of done whatever I was interested in at the time. Finished my undergrad, thought I'm really enjoying this. I'll go and work in the lab for a bit. Worked in the lab for a bit, thought I'm really enjoying this. I might as well keep doing it as a PhD. Did a PhD, thought, well, I like what I'm doing. Maybe I should do more science. Did a postdoc, and I was like, yeah, I still like what I'm doing. Maybe I should try and do this forever. I don't think you need the level of planning where you have it all mapped out at the beginning.
Yeah. Surely it can't steer you that wrong if you just do what you enjoy.
Yeah, that's right.
Absolutely.
Exactly. It's exactly the philosophy I subscribe to. Just keep going while you're having fun.
Exactly.
Well, on that note, I'll say thank you very much, and
Thank you.
hopefully you'll come back next year when you talk about some more of your Martian and lunar results.
Okay,
and,
that would be great. Yeah, I'd love
yeah.
to.
In the meantime, thank you very much, and we'll see you all next week.